Okay. Okay, so our major, we're going to talk about major versus minor losses in pipe flow. And we've been discussing major losses up to this point. Is there larger, right, energy loss due to friction and pipe flow. And then we calculate this using Darcy-Weisbach equation or empirical equations. That friction is from pipe walls or water essentially just rubbing up against the pipe wall, right? And if we have a mile-long pipe, we have a whole mile in which that friction occurs. But we get additional losses occur when our streamlines change direction. And for example, when we go through a bend in a pipe flow, we have water flowing through here and we have a bunch of streamlines. And granted, it's turbulent flow, but they're changing direction. So it's not, if they're parallel, it's laminar flow, and we typically don't have laminar flow. But they're changing direction, and then there's a lot of like additional turbulence that happens when they change direction. And we'll look at some CFD images, some computational fluid dynamics images, like modeling of this to see what that looks like. And this occurs in a lot of different examples. I'll give you like the whole list of them, but essentially bends or contractions, expansions, that sort of thing. So let's bring our minor losses into the energy equation. And let's write out the energy equation together. And let's say it together, because we're going to memorize it. So P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2. And then let's throw in our Darcy-Weisbach equation plus F L over D V squared over 2G. And these are what we're calling our major losses. And then I'll give you kind of a generic equation that mostly holds, but I'll give you kind of all the examples. Plus our minor losses, which is some coefficient. And we're going to sum them all up because there might be 3 bends and 1 valve and 1 expansion and 1 contraction. So we're going to sum all those K values associated with different minor losses times V squared over 2G. So this term here, where we sum up, you know, everything that might happen in a pipe system, we'll call that our minor losses. And just as an example, we could have 3 bends, 1 expansion, 2 valves, right? So we'll show how this actually plays out numerically. So just to note about minor losses, that they're all proportional to the velocity, typically the velocity head. So that V squared over 2G term. And then the magnitude of the loss is described by that K term. Which is just called a minor loss coefficient. So let's look at some minor loss examples. Okay, here's our tables that we learned for the empirical equations. So this is going to be loaded on Canvas. So you'll have that. We'll get through our type 2 problem. There we go. So let's look at minor losses. What's actually happening here? We're losing energy, but it's minor. It's smaller than what you lose energy over hundreds of meters or many miles of pipe. And what we're seeing here are outputs from what's called a computational fluid dynamic model, CFD, where they are solving that really complicated Navier-Stokes equation, which maybe you were introduced to in fluid mechanics. But it's basically the equation for three-dimensional flow. And it has to be solved numerically. It's really computationally intensive. Carrie did a bunch of this for her PhD. And I just looked at the pretty pictures that came out of it. So what it does is what we're seeing are these tubes are basically streamlines. They're tracing a particle of water as it moves through a pipe. And here's a bend, and what we see is that as the colors represent the velocity of that tube or that streamline or that particle. What we're seeing is as you approach a bend, things get twisted. There's this kind of vortex that sets up. This is a slow or low pressure zone, or sorry, a slow zone. And then we have a high zone, and then we get this kind of turbulence that happens after the bend. So it's not this like continuous perfect field of flow as things go around a bend. There's actually a lot of kind of complicated hydraulics happening inside. And across that bend, we're losing energy because of the streamlines twisting and turbulence and all that. Here is flow going through some kind of Venturi meter. So this is basically a contraction and then an expansion. And then here is flow going through, I think, like a valve. So it's basically a gate that's kind of coming in, and you can see where it's pinching the flow and it's accelerating around the gate. And then you get this wake zone or eddy that happens behind the valve. So energy loss is happening because of that turbulence. That's kind of a bit of the hydraulics or the fluid mechanics that's happening behind that. This is looking at pressure. So CFD models can model velocities and streamlines. They can also model, using the energy equation, pressure distributions. So here's a high pressure zone on the outside of the bend, a low pressure zone on the inside of the bend. And when you have that gradient of pressure as well, that kind of describes the fact that you're getting energy losses. So higher pressure here, lower pressure here. That pressure change means we had an energy loss in the pipe. Same with this flow. So the flow is moving this way, higher pressure. We go through the bend, two bends, and we get lower pressure. So we lost energy. So you can model this using CFD. You can also measure it. We'll do a lab on Wednesday where we measure that energy loss. I think we have a video here. Let's check it out. No, not a video. Oh, maybe it is. Let's see. Oh, okay. Guess not. All right, so let's look at how this plays out. And we'll just go through some examples. You've got this handout here, but I just want to orient you to how this works. So the first thing we'll look at is a contraction, a sudden contraction, meaning a right angle contraction. And that's contrasted to a gradual contraction. And we'll look at that in a second. But what do you think you lose more energy at, a sudden contraction or a gradual contraction, where you basically have a smooth transition from a large diameter pipe to a small diameter pipe? Yeah, you use more of the sudden. You kind of think of rough angles as like causing more friction or more turbulence. That is why if you look at our HVAC system, you see gradual contractions. because this is a pipe flow problem. Different density fluid, but we want to make sure we can maintain pressure all the way to that very last register so that we get the flow rate we want out of that. So HVAC is very much consumed with losses and pipes and making gradual transitions as we go from one size pipe to the next. Because again, if you just had a right angle and a really sudden contraction, then you're going to lose pressure and you're going to lose energy, and so you're going to have less pressure at the end of the system to deliver that air. So to do a sudden contraction minor loss calculation, the head loss is calculated as this coefficient times v squared over 2g, but which velocity are we using? This isn't very tricky except for which velocity do we put in the equation. In this case, it's the downstream velocity or the faster velocity for the smaller pipe. So v2 squared over 2g, the velocity in the downstream end of the contraction. And our coefficients are a function of the pipe flow velocity in the smaller pipe, so v2, as well as the ratio of the diameters. And you can see that we get really big, so let's see here, as velocity increases, our coefficient is decreasing. And then as our ratio goes to 1, our coefficient decreases. So as we get a really big difference between the upstream and downstream pipes, we get a bigger coefficient, versus obviously they're really similar, we get a smaller coefficient. So those are our diameters, and then that's our downstream velocity that we use. Here's our gradual contraction. There's going to be an angle associated with that. So the angle is, I guess it would be the angle if you were to take this all the way down to a point. I'm sure that's going to be something that would be specified. We've got, instead of a table now, we have a graph, a nomograph, and we've got different areas. So the ratio of areas instead of diameters, so it's a little bit different. So area, let's see here, area 2 over area 1, cross-sectional area. And then you've got these lines based on that area, and then you pick your K value based on the angle of that transition. And then you would just come over and trace over to get your KC value, the contraction value. Notice that it's the downstream velocity that we're using. We also have entrances to reservoirs, so you'll see this in some problems. There is an energy loss if you're in a reservoir because you have water that's not flowing that's moving into a pipe that is flowing water. So it's just there's an entrance coefficient depending on the type of entrance. This is the default, just like a square entrance. You could have a curved entrance, and you multiply that v squared over 2g, and that's the velocity of the flow in the pipe. Here's enlargements, a little bit different. The coefficient is based on the differences of the velocities squared over 2g. Here's a gradual enlargement. Similar, the differences in the velocities times a coefficient based on the angle. That's the angle that we would use. An exit to a reservoir is just going to have one coefficient, so we just 1 times v squared over 2g. So that's water flowing out of a pipe into a reservoir. And then we have losses at bends. And so the bend loss equation, we don't have an expansion or a contraction, the pipe stays the same, but we do have a radius of curvature. So this is the radius of curvature divided by the diameter of the pipe. And then that gives us our coefficient. Finally, we have losses at valves. There's going to be valves in different systems. The flow, even if the valve is fully open, there's still going to be some turbulence and loss to that valve. So here are the K values for different valve types. And typically that's going to be specified. Is it fully open, fully closed? That sort of thing. Or sorry, it would make sense if it was closed, right? So here we go, open. And they're specifying fully open because you can crank a valve partially and there's going to be more energy loss if you crank a valve down partially. Okay, so that is, so let's do an example problem with minor losses. And we're going to go back to that same example, because why not? Where we had two reservoirs. And this is what we did previously in a previous lecture, but I'll just set it up again real quick. We had two reservoirs. We had a difference of, let's see real quick. There we go. We had a difference of 10 meters in the water surface elevation. We had a diameter of 0.5 meter. We had a length of 700 meters. And then this was a cast iron new pipe. And water flows from A to B. And we calculated this last time. We got a flow rate of 0.56 cubic meters per second. Using the Darcy-Weisbach approach to head loss. Now we want to calculate, so we just, this is our major losses right here. All right, but now that we have this flow rate, let's actually calculate some minor losses here. And we'll put some more information on here. So we're going to put a valve on that. And the valve is going to be a swing type check valve. And then we're also going to account for the entrance and exit losses. So H minor is going to be equal to, as we said before, the sum of our minor loss coefficients times V squared over 2G. And so in this case, we're going to have an entrance coefficient. We're going to have a valve coefficient. And then we're going to have an exit coefficient. And all that's going to be times V squared over 2G. This is a pretty simple problem because we don't have different velocities. We'll do a problem later in class in the next week or so where we actually have to use minor losses in the iterative scheme because the velocity, we're solving for velocity, but the minor losses are also a function of velocity. So that's going to be a challenge that we'll broach later. So we can go to the handout that I gave you all, but we also have this in our book. And we can look up our coefficients. So K-ent coefficient is equal to 0.5. The K-exit coefficients is equal to 1. And then given this type of valve, that coefficient is equal to 2.5. This coefficient is based off of a square entrance where we basically have a situation that looks like this. And unless it's specified otherwise, we can just assume that. So now all that we have to do is solve for velocity and plug these numbers in. So velocity is equal to Q over A is equal to Q over pi d squared over 4. So let's plug our values in. And then we get a velocity of 2.85 meters per second. Okay, so now we can plug all of our values in. H minor is equal to our entrance value, 0.5 plus 1, our exit value plus the valve, 2.5, times v squared over 2g. And then we do all that and we end up with a minor loss of 1.7 meters. So this is typically, a small value in a system, in a pipe system, the minor losses are. Quickly, we'll compare that to the major losses. And that is equal to what we can calculate with the Darcy-Weisbach equation. From the previous problem, I'll just plug in these values. 1.0175 times 700 meters all over 0.5 meters times 2.85 squared over 2g. And that ends up being 10.1. So in this case, we're about 20% or a little bit less for the minor losses compared to the major loss. The major loss is always much more, usually by many factors. But maybe not necessarily in order of magnitude. Depends on how big the system is and how long that is.